Welcome back, Calculus. We're working on 4.6. And what we're going to do is make connections between the original function, its first derivative, and its second derivative. This is just the first part of this. And we will have another test coming up. So just as a quick reminder, just remember what we've learned about the connection between the function and its first derivative. And the main thing to mention there is if f is increasing, now I'm going to put a double-headed arrow because if f is increasing implies that the derivative is positive, and then vice versa. If the derivative is positive, that means that f is increasing. And I can just flip that. If f is decreasing, that would imply, again, I'm going to put double arrows. Now, if the first derivative is equal to 0, we can't tell for sure if it's increasing or decreasing. It's a horizontal tangent, but if it goes from increasing to increasing, we just say it's increasing throughout, or if it's decreasing to decreasing. So notice I don't have that equal to 0. Kind of important. So what we can do is we can look at these problems, and we're just going to change something just slightly. But the first thing that they want you to recognize as we look at G in this problem is at what values do we have a relative max or min. So I'm just going to point out at x equals 0, we get a y value of 0 is our relative max. And then maybe just to change colors, the relative min, it looks like at x equals 2. By the way, you only have to give the x value, but I'm just giving you the ordered pair, 2, -4. And that's based off what it looks like. And you could verify because 2 cubed is 8. 2 squared would be 4. 3 times 4 would be 12. And 8 minus 12 equals -4. But anyway, what we're going to examine now is the derivative of G. So if I were to ask you to find the derivative of G, we would get 3x squared minus 6x. And with these x values, let's see what happens. Well, if we did g prime of 0, well, 0 squared still 0 times 3 still 0 minus 0 equals 0. And the same thing could be said for g prime of 2. Now, a little bit more work probably should be done. 2 squared is 4 times 3 would be 12, and then 6 times 2 is 12. So we still get 0 there. And the whole premise of doing that, sorry, as I move the screen around, is this value, is that if the first derivative is equal to 0, it's our clue that a relative min or max could occur. It doesn't have to occur, but it could occur. So what we do is we call these critical numbers. So x equals 0 and x equals 2 are critical numbers. And I can do the same thing with the graph of f over here. So just to change colors, there's no max in this problem because right here at about -1, 2 looks like the only minimum. And so when you find the derivative, oops, I wanted you to see the graph, the equation I should say, it is the chain rule except the derivative of the inside is just 1. And as a reminder that this is the same thing as 2 over 3 cube root of x plus 1. And if you were to plug in the x value, which is -1, let me just squeeze it right here. Well, this time we get a value of does not exist or undefined. So what they want you to do for f here is to perform a sign analysis for f. I guess I could have done it for g as well. And what I want to see from your sign analysis is what we've practiced before. So if we were to plug in, say, a -1 in for x, so -1. Now, if you put in a -1 in for x right here, we'd be dividing by 0, so it'd be undefined. Well, what you also want to think about is if you had a negative value, so like -2, -3 right here, well, what would end up happening is you would have a positive divided by a 3 times a negative number would give you a negative. I guess I should mention that the cube root of a negative is still negative. So this is what we're talking about for a sign analysis is, and if you wanted to, you could write that 2 is positive in the numerator, and a positive divided by a negative is still negative. Whereas if you had a number to the right of -1, let's say 0 or 1 or 2, and you plugged it in for x, well, now you have positive 2 on top divided by some other positive number. Because if you had 0, it would be the cube root of 1, the cube root of 2, the cube root of 8. You know, they're all positive numbers. The cube root of a positive is positive. So the reason why we do a sign analysis for the derivative is saying that, well, if the derivative is negative, then we're going from decreasing. And if the first derivative is positive, we're going to increasing. So what's the only way to go from a decreasing to an increasing problem is if x equals 1 is a relative min. Why? Let's put a quick because here. F prime of x changes from negative to positive. And that should be your reason when you're explaining why you have a relative min or a relative max, is you want to look at the sign analysis for the derivative. And I could do the same thing for g as well, but we have plenty of examples, and I don't want to overburden you with a lot on this first page. Okay, so defining critical numbers. Let me pull up the answer key, actually. I think it'll be better if I just give you that. Again, it's probably just easier if I just explain it this way. So a critical number is a value of x where a function's derivative is either 0 or undefined. Because if you have an undefined derivative, it could have a sharp turn like the example we just did. And if we have a sharp turn, it could have a sharp turn at a minimum value or a maximum value. So notice that the key word here, though, is potential relative min or max. Because what you could have, and if you think about like a cubic function, just y equals x cubed, at x equals 0, the derivative equals 0, but it's not a min or max. So that's important to mention there. So our critical numbers will only find potential. And if that derivative is positive, that's what this statement is saying, then the function must be increasing. If the derivative is negative, that function must be decreasing. And the only way to have a relative max is if the derivative changes from positive to negative. And likewise, for a relative min, it only happens if the derivative changes from negative to positive. So pause the video, and in a few seconds, I will go back to the notes and just continue on. Actually, I'm going to just kind of remind you of what we did in pre-calculus, but then I'm going to quickly forget about this. So don't feel the need to write this down, but we're going back to the graph of g, and you may remember in pre-calculus that we talked about inflection points and how inflection points happened halfway between relative extrema. So you can see the work that he did here with the midpoint of those two values, and we talked about concavity being a downwards U, so it's concave down from negative infinity until we got to about 1, and then it's concave up from about x equals 1 to infinity. Well, now what we're going to do is we're going to find the exact point of inflection. Okay, so we're going to do the second derivative of g. Let's go back and remind ourselves. G was x cubed minus 3x squared. And the first derivative we found as 3x squared minus 6x. And when we set that equal to 0, and you could factor out a 3 and an x, we found that the relative extrema occurred at x equals 0 and x equals 2. But what I'm going to point out now is if I ask you for the second derivative, it actually makes sense to go back to the first derivative, which would be 6x minus 6. And if I set that equal to 0, and then solve for this, add 6 over and divide by 6, you get x equals 1. Now, just because we have x equals 1 does not necessarily mean, I guess, everything that it's just a potential point of inflection, I guess I should say. But if you perform a sign analysis at x equals 1, so right here's at 1, and again you can plug in values like 0, -1, -2, and you'll see you'll get a negative value over here. And notice I'm doing the second derivative. I'm plugging into the second derivative, and a positive to the right of x equals 1. So what that means is that it is concave down. When you have a negative in the second derivative, you get a concave down graph, and a positive to means it's concave up. So as a reminder, I'm not a big fan of how this author wrote his sign analysis, because he does specific values and that's not good enough on the AP test, but it does help some students, so I have no problem sharing that. But he actually gives out the reason. If in your reason needs to be the second derivative is negative, the graph of g must be concave down then. So then it's concave up from 1 to infinity because the second derivative is positive. And maybe you remember, maybe you don't, but the actual definition of a point of inflection is if it changes concavity. So if the second derivative changes signs, that's the actual reason why it's an inflection point. And some teachers are kind of mean about this. When a person asks for a point of inflection, you technically should give an x and y value because points have x's and y's. Well, that's an easy fix. You can go back to the original function and plug in 1 in for both those x's. So it'd be 1 minus 3, which is -2, as was predicted. So here's your next set of definitions. If your second derivative is 0 or undefined, it has a potential point of inflection, potential being the key word. If the second derivative is positive, then the function is definitely concave up. If the second derivative is negative, it is concave down, f in this case. And the only way to have a point of inflection is if we change concavity, so it doesn't matter if we're changing from positive to negative or negative to positive. And this might be a good place to stop my video, and then I can pick up on the next one in the next video.